let's introduce the field of statistical estimation with a classic problem called the German tank problem, also called the locomotive problem. So I'll state it in this sort of World War II context, which is pretty common for writing this problem down. 3 enemy tanks with serial numbers 121, 53, and 246 are captured during the course of a war. Now we're assuming these tanks are produced on a single production line, and they come off the end of the production line with serial numbers that are just sequential whole numbers starting at 1. So the first tank that was produced of this type, it has serial number 1, the second tank has serial number 2, and so on. So the task is to estimate the total number of tanks of that type that have been produced. And before we formalize this problem mathematically, which is what we're going to do, before I reveal how I'm going to do that, I want you to just think about this problem for a minute and think about how you'd answer the question. Can you come up with a reasonable, what is in your mind, a reasonable way of estimating the total number of tanks that have been produced, given only these 3 numbers? This is what statistics is all about. It's about reasoning with partial information. All right, and you'll see it feels like a very open-ended question, and it is a very open-ended question. And if I ask 2 different people to come up with an estimate, they'll probably do it in 2 different ways, and they'll probably both be uncertain about their answer. And that's good. So, to analyze this problem, let's formalize it mathematically, all right, by doing this. So, think about the distribution of serial numbers on the tanks. So if I just randomly pick a tank of that type, and I look at its serial number, that's going to be a random variable. And what's the distribution of that random variable? Well, if you think about it, it is a uniform distribution, a discrete uniform distribution. I could get tank with serial number 1, I could get the tank with serial number 2, and so on. And I could get the tank with serial number M. I'm going to let M be the biggest one, the biggest serial number. So this is the tank that has most recently been produced. It has serial number M. And all of these occur with equal probability because there's 1 tank with each possible serial number on it. And if I'm randomly selecting a tank, I'm equally likely to get any of the tanks. So, an equivalent way of stating this problem in a little bit more formal language. Let x be a discrete uniform random variable with parameter m, that's the maximum value. Remember, this is shorthand for a uniform distribution on the set of values 1, 2, 3, 4, the whole numbers starting at 1 and going up to m. Given a sample of values drawn from that distribution, estimate the parameter m. Okay, so in order to make progress on that task in a deductive, rigorous mathematical way, we've got 2 new ideas here. We know all about the discrete uniform distribution, all its properties, random variables, all that stuff. The 2 new ideas are the sample of values. We need to describe mathematically what does it mean to get a sample of values. Where did these values come from? I need a precise mathematical way of describing these 3 numbers. How did I get them? Where did they come from? And when I actually come up with my estimate, what does it mean for my estimate to be a good one? Because I could just say, okay, you give me the 3 numbers, 121, 53, 246, I go, okay. I estimate that the number of tanks that have been produced is 311. What does it mean for that estimate to be good? Well, if I just give you the number out of nowhere, there's no way of evaluating that. The only way to evaluate that would be to know, I would have to know more information. I would have to know, well, if it turns out there are 315 tanks of this type in total, okay, that's a pretty good estimate because 311 is close to 315. It's a really good estimate. But I don't know the total number of tanks that have been produced. That's the whole point. That's why I'm estimating. So I have to come up with a way to convince myself that the method I used to come up with my estimate is a reasonable method without actually knowing the value that I'm trying to estimate, because otherwise I wouldn't have to estimate it. So those are the two things we need to do. Thing number one, describe the sampling process mathematically. Thing number two, decide on how to measure whether our estimate is a good one. All right, a few things to say here. In the sampling process, you got to think about where did these three values come from? And there's a lot there. We're not going to talk about this and go too deep into this issue in this course, but we're going to assume, in the future we're going to do this, you'll see, that this sample is a random sample for the purposes of making the evaluation of making the second part easier. Because in the real world, there's a great deal of value on making accurate models, not of the estimate that we're going to come up with, not of accurate estimates, but just accurate models of where these numbers came from. Just take in this problem, for example. If you think about it, these are probably not randomly selected tanks, the tanks that we captured. Why? If you have a tank with a small serial number, that means it was produced a longer time ago, which probably means it participated in more battles, which probably means you're more likely to have captured it, because it's more likely to have been in a battle that that side lost, and that therefore you captured the tank. Also, it's an older tank, so maybe it's less reliable, it breaks down more of the time, and so you captured it for that reason. So this sampling process, describing the sampling process mathematically, this is a huge deal. And polling firms and places like 538, 538 is a site that does political predictions as well as many other predictions. Their industry is this. It's having really good models of the sampling process and being able to oftentimes themselves do a sampling process. They do the sampling, and really knowing a lot about the details of where these numbers came from and how far from being random numbers from this distribution they are. All right, anyway, lots of issues here. But for us, you'll see in the notes and in the next video that we're going to assume the sampling process is sort of the simplest possible one. And we're going to answer all these questions with that assumption, that these really are three randomly selected tanks. Okay, right. And so I want to actually contrast this problem, the German tank problem, with a different problem, which at first glance, this seems like a very open-ended problem. On the other hand, if I were to just ask you this, it seems like there's a more of an obvious thing to do. 3 students in a certain classroom have the ages 17, so a 17-year-old, there's a 22-year-old, and an 18-year-old. Estimate the mean age of all students in the classroom. Well, I expect what a lot of you would do is you would say, well, I have this little sample, and if I take the mean age in my sample, so I add up all the values and divide by 3, I take the average of these 3 values, I get 19. We'll say, well, I have the sample of 3 people from the classroom, and assuming they're randomly selected people from this classroom, then it seems reasonable that I should use the average age of these 3 people in my random sample as an estimate for, I'll call this mu, which represents the mean age of all students in the classroom. Notice, however, that in fact this problem is actually more open-ended than the German tank problem. Why? Because in the German tank problem, in both problems, we're estimating the value of a parameter of a distribution. In this case, it's the mean. Estimating a property of an unknown distribution, let me say it that way, from some sample data. But in the German tank problem, I knew a lot about the distribution. The distribution of serial numbers on a randomly selected tank is a uniform distribution. Very I have a very good idea of what that looks like. However, if I think about the distribution of the age of a randomly selected student in this classroom, I don't know anything about this classroom. I know this distribution could be anything. It's almost certainly not uniform because there's probably not a 1-year-old in the classroom. It could be kind of bell-shaped, it could have 2 bumps, it could be, I don't know, like, it could be all kinds of crazy things. So it's interesting to note that in this context, it seems sort of intuitively obvious that this is a good thing to do. Whereas in the German tank problem, when you first read it, it's really not at all obvious. There's no sort of first thing you think of like, oh, immediately you should do that for most people. So this is nice because this is good. This is a really good way of estimating the mean age of all students in the classroom, to use the average of my sample to estimate the average in the whole classroom. But why? You would probably do that, but why? So we're going to try and think about why. And we're going to, when we see the reasons, the mathematical reasons, we'll be able to apply those reasons to the German tank problem as well and say, oh, can I come up with a method of estimating the total number of tanks that have been produced that is a good method in the same way, the same mathematically precise way, that we're going to see that this is a good way of estimating. Using a sample average is a good way of estimating the average of age of all students in the classroom.